All right, so it's my great pleasure to introduce Jeff Heer. Jeff is an associate professor of computer science at the University of Washington, and he actually literally just flew in. His plane was delayed because of the cold, I believe, so we're very lucky that he made it in time, and now he has to deal with some technical difficulties. But he was MIT Technology Review's TR35 in 2009 and the Sloan Foundation Research Fellow in 2012. Jeff's also a personal hero of mine because he developed, among many other things, D3, a visualization tool, and then ProtoVis, Flare, Prefuse before that. And he's got a PhD in computer science from the University of California at Berkeley. So let's all welcome Jeff.
Thank you. Good morning, and I'm really glad to be here. As Hans-Peter said, my name is Jeff Heer. Actually, for the last 5 years, I've been at Stanford, where I ran the Stanford Visualization Group, though lately I've traded in my cardinal and instead gone for a more royal hue. So I'm at the University of Washington. And so what my group works on is what we call interactive data analysis, which is basically focusing on the people who are working with data and tools to better support them. So for example, making expert data scientists more efficient or helping novices achieve results more like experts. And so along the way, we take inspiration from many sources, one of which is the statistician John Wilder Tukey, perhaps the greatest statistician of the last half century. And he's had many writings that have been influential to me, including an overview article written back in the mid-60s, along with Martin Wilk, on data analysis and statistics. And I wanted to start off just by sharing with you some quotes from this paper. So first of all, he wrote, 4 major influences act on data analysis today. 1, the formal theories of statistics. 2, accelerating developments in computers and display devices. 3, the challenge in many fields of more and larger bodies of data. And 4, the emphasis on quantification in a wider variety of disciplines. So clearly the mid-60s were a very different era from today. Interesting. So he goes on to write, perhaps most interestingly coming from a statistician of his caliber, while some of the influences of statistical theory on data analysis have been helpful, others have not. Exposure, the effect of laying open of the data to display the unanticipated, is to us a major portion of data analysis. Formal statistics have given almost no guidance to exposure. Indeed, it is not clear how the informality and flexibility appropriate to the exploratory character of exposure can be fitted into any of the structures of formal statistics so far proposed. Nothing. Not the careful logic of mathematics, not statistical models and theories, not the awesome arithmetic power of modern computers, nothing can substitute here for the flexibility of the informed human mind. Accordingly, both approaches and techniques need to be structured so as to facilitate human involvement and intervention. And so I think what Tukey's arguing here is obviously not against statistics, but rather understanding the arsenal of tools that we have at our disposal to really make data actionable and useful to us. And he's also along the way sort of written a manifesto that probably better than I could write for myself for why I think questions of human-computer interaction, data visualization, and the role of the analyst within the process of making sense of data is so important. So let's look at one example here. Here's a relatively simple data set, but one that may be close to home for many people. This is actually a visualization of data extracted from Facebook. So this is an ego network. In fact, this is my ego network from a couple years ago. So it's basically all the connections between my friends with myself removed. In this case, circles represent people, lines represent connections between them. And in this case, the people or circle nodes have also been sized by a statistic called Betweenness Centrality, which gives us a sense of how central an actor is within the network. And looking at this diagram, this is an example of a node link diagram or a graph layout, gives us some insight into this data. And oftentimes we want to use visualization to get a sense of the structure and shape of our data, for example, to refine our hypotheses or to inform modeling assumptions. Here we might notice 3 big clusters, 2 small satellites, and then this big blob in the middle, which turns out actually corresponds to many of the people I met in grad school and research over the years. But beyond that, it's sort of difficult to see more delicate structures within the data. Some of you familiar with social network analysis may recognize that this big blob has core periphery structure. This is a denser core surrounded by a lighter periphery, a very common pattern in social networks. But beyond that, it's really hard to see deeper. So what can we do? Well, in addition to modeling, there's, of course, many different visualization techniques as well. So we might look at this data from a different perspective. So for example, this is an adjacency matrix, where now we've put the edges front and center, and people are now rows and columns. So basically, we have people as rows and columns, and then we fill in the cell if there's an edge between them. And then in addition, to help see structure, we've also applied some analysis, in this case a statistical algorithm or optimization approach called seriation, where we permute the rows and columns to try and put highly connected actors next to each other. That's why we want to get this clustering structure along the diagonal of the matrix. In doing so, we can start to see interesting patterns that previously were hard to spot. We still have those same satellites as before, in this case in the bottom right or in the mid left, upper left here. But we also see that giant blob breaks down into 3 components. So there's 2 in the center here and then 1 in the upper left, and we can see the connective tissue basically between them. And that's actually pretty interesting. It actually breaks down into the human-computer interaction research community, the UC Berkeley Computer Science Department, where I got my PhD, and the UC Berkeley School of Information, where I spent the other half of my PhD. And at this point, we might say, great, now we have a deeper understanding of this structure. We kind of have an intuitive sense for the data. We might then apply any number of formal methods as well to analyze it. But I'd actually caution you from going ahead and doing that at this point, because while we've seen this nice representation of the data, it's also really important to look at the data in its rawest forms. And that might include just raw bits and bytes or simple visualizations that show us something about the basic structure of the input. So for example, instead of doing this fancy sorting of the matrix, I just plot it as it arrived, which in this case is sorted by the Facebook ID number. I see something quite striking that was missing in the previous 2 displays. So in this case, both the rows and the columns extend basically by increasing Facebook ID, which you can really treat as a counter that tells you when a person joined the service. So if we were to take this visualization at face value, what it tells us is that all the newcomers to Facebook don't friend each other. Right, and you're giggling, right? Maybe this seems sort of ridiculous, and so we might have some anecdotal evidence that would suggest that that would be a false inference. So instead, what actually happened here? Well, this forced me to do some digging. Turns out what happened is I wrote a single query to the Facebook service to get all the data with subclauses and everything, thinking about how clever I was, not realizing that Facebook silently imposes a 5,000 element result limit. So had I naively write a query for every one of my friends, I would have done much better. But in this case, we have a problem of missing data, not just in terms of missing values, but actual missing records. It may be something to 15 or maybe even 20% of the data may be missing, which would undermine any modeling efforts that we then might engage in. So again, the idea is to understand how facilities such as visualization, along with formal methods, can be best combined to enable effective analysis. And obviously, I think one piece of that puzzle is visualization. So basically using visual representations of data to help them make them more accessible to us and allow us to reason more effectively. But what these examples also shows that there's much more than visualization involved in the data science process. And as you well know, this includes things like acquiring data, cleaning it, integrating diverse data sets, engaging in exploratory and confirmatory analyses, and also sharing and disseminating results. And many speakers, of course, will be touching on these issues throughout the day. And I think one thing that we can say for certain is that as much as we'd like the process to move like this, in reality it's much more like this. For example, as we saw, we might start visualizing data, realize that we have flawed assumptions, or we need to go out and acquire data, made errors in integration, etc. We need to understand how these iterative and interactive loops in the process unfold and how we might design better tools to support them. So given that framing, what I'd like to do in the rest of this talk is share just a handful of projects where we try and identify bottlenecks in the life cycle of data analysis and create new interactive tools to try and address them. So let's start more towards the beginning of this process with issues of data cleaning and preparation. So when we were starting this research project, we actually went out and did interviews with lots of data scientists. So we went into a number of different companies out in industry and observed what people did. And here's a representative quote that came from some of the interviews that we conducted. I spend more than half of my time integrating, cleansing, and transforming data without doing any actual analysis. Most of the time, I'm lucky if I get to do any analysis at all. And while this is, perhaps a sob story, it's a true one. And in fact, he has it good because most of the folks we talked to said something that was more around 80% of their time was spent in these low-level data preparation tasks. And this is true of my own practice in visualization as well. For every interesting visualization I built, I probably actually spent more time prepping the data than I did actually designing the visualization. And so across these different areas, I think of data preparation as something of the elephant in the room of data analysis work, something that we're all doing, but only recently have folks really begun to talk about it in earnest. And this isn't just dirty data or unstructured data. Even relatively clean and curated data suffers from some preparation issues. So for example, consider your taxpayer dollars at work here. This is crime statistics from different states about housing crime produced by the Bureau of Justice Statistics. And while nicely formatted and great if you want to look at it in Excel, I encourage you to go ahead and load this into R or a database or Tableau or any visualization tool and see what happens. It'll just break on input because it has an idiosyncratic format. So what can we do? Well, right now, people spend hours manually manipulating data in Excel if it's small enough, or writing one-off scripts that they throw away in languages like Python and Perl. Can we do better? One, not only for replicability, but also to make this data transformation task accessible to a larger audience of folks who may not have the same level of programming sophistication as experts. So this led to a number of research projects, one of which I would like to share with you today called Data Wrangler. This was primarily the work of my PhD student, Sean Kandel, who recently graduated from Stanford. And let me just jump right into a demo to show you how this works. So here's the basic Wrangler interface. You could upload data in various ways. You might be sitting on a cluster or on a server. You might upload it. In this case, for demo purposes, we'll just copy and paste a relatively small data set into the system. And you'll recognize this as a simplified version of the housing crime data we just saw. So I click Wrangle, and then I load this into an environment. And so we see the data table on the right, and in the bottom left, we can actually see operations that have been performed. So in this case, 2 actions have been taken already on our behalf. So splitting the data into rows and into columns because it recognized the data type. In this case, the column structure of the file. If it hadn't done that, we could do this ourselves, or we could even undo this if this inference was an error. But let's just get busy cleaning up the data. We initially see that there are empty rows, and we'd like to get rid of them. So rather than search through different operations, let's just go ahead and show that we're interested in this row. So clicking it actually initiates a search over possible operations that you could perform on this data table. One might be to just delete that row that you selected, but the tool can also see that that row is empty, and so generalizes that selection. I hit the down arrow to get the next suggestion, which is delete all empty rows. In this case, you see we use red highlighting to visualize the effect of this transform before the analyst commits to it. And this is what I want, so I'll go ahead and hit Enter. And now my data table updates, and I have a new command in the bottom left. Now, next thing I would like to do is get the state names out of those headers and associated with the actual data rows. So I can go ahead and select the text Alabama, because I'm interested in those states. In doing so, the system infers that I'm trying to do an extraction, and that's correct, but it initially starts with very basic extraction parameters, in this case by indices into the string, the next one being exact string matches, which would be great if I wanted to count all instances of Alabama, but that's not my task. So rather than get bogged down in the suggestions, I can actually just start giving more examples by selecting more states. This provides additional examples from which we can generalize a variety of regular expression patterns. In this case, the top ranked one is to extract the word after the text in, which for this data set is exactly what we want. So we can read that transform, we can look at the view to see what it's doing, we can even scroll through more pages of the data if we wanted to assess further. So now that we've extracted this text, we can go ahead and hit Enter, and now we have a new column with the state names, but obviously it's largely empty. And as I'm doing this, you may have been noticed that there's some other things going on. There's a number icon here, as we've inferred that this column is mostly numbers. And then in green, we show the percentage of values that actually parses numbers. And then in red, we can select all the things that don't parse according to the inferred data type. Similarly, on this column where we extracted the text, we have a large percentage of missing values indicated in gray. So I click that, I can get suggestions for ways to deal with those missing values. Now, it's probably a pretty poor suggestion to have number 1, delete everything. So obviously, there's still some room for improvement. But the next things, of course, are interpolation. So in this case, for string data, we can interpolate by copying. So fill up or fill down. Fill down works well here. Now we're getting close to data we could actually import, but we can get rid of these rows that we no longer need. So we could, of course, delete things that don't parse as numbers or delete cells that are empty on the far right. But those are brittle transformations. Like there may be empty values I'd like to fill in. There may be typos that don't parse as numbers, but I would like to fix. So let's be careful, and we'll make a slightly more robust transformation. We want to get rid of all the rows that start with reported crime in. So we select that text, and then Wrangler thinks we're trying to do an extraction based on the length of the selection we made. But we're not. We can give it a hint and tell it that actually what we'd like to do is delete data. Doing so, it causes it to update its search, and now we get basically a deletion operation with the right predicate, the text with the reported crime in at the beginning. So that's great. So now I hit Enter, And now I actually have my data in a nice format I can load into other tools. And I'll spare you the minor effort of renaming all the columns here. So what we could do is go ahead and export this data. Because it was relatively small and I was able to manipulate it all in browser here, I can just export it directly as CSV or JSON or any variety of data formats. But perhaps more interestingly, there are many, many data sets, obviously, that wouldn't fit in memory in a web browser to allow you to interact with them. But we can, however, bring in sampled rows of those data and then clean them up in this tool. And then doing so, we have this history of operations. And what you're seeing here as sort of pseudo-natural text is actually just renderings of statements in a high-level programming language of our own design. So we can take that and cross-compile it to basically any language we want. So for example, I can generate code that actually implements the transformation we just demonstrated in Python. Or I could export it as JavaScript to run on Node.js or as Postgres queries to run in a database. Within the lab, we've also done a generation of MapReduce programs to run these transformations at scale on a cluster. And so the idea here is to be able to move the kind of onerous task of data transformation into something interactive and visual, but in a way that still supports scalable data transformation for the data volumes that we're dealing with today. And Keynote. So that's Data Wrangler. If you're interested, just type Data Wrangler into Google. You'll find it online. The service I just demonstrated is up, free for use, and there's also all the source code is open source under a BSD license. So that's one example of the way we can start bringing interactive tools into the data analysis process, this time around cleaning. And once we get the data cleaned up, we can really start having a lot more fun and getting insights into the data. And so one of the ways we can begin to explore new data sets is obviously through visualization. And there are many, many interesting research challenges in visualization. This is actually one of the primary focuses of my work, much more than I can talk about today. I want to focus just on one question that's really motivated us for a number of years, which is, how might we best support expressive and effective visualization designs? So we want to be able to create visualizations quickly so that we can be agile in our exploration processes. But we also want a really wide expressive space so that when we're creating visualizations, particularly for communication, whether that's to communicate to our peers, to create presentations, or even in the use of data-driven journalism, we want to be able to communicate effectively and explore a variety of designs. So let's look at some examples of what I mean with that. So let's say goodbye to Wrangler, and we'll look at some different examples of visualization. So one of the fun things about visualization is, like many other academic fields, it has a long history, actually spanning millennia. That was really only in the last couple centuries that we see kind of the standardization of common statistical graphics today. And one of those innovators was actually the Scotsman William Playfair, who over 100 years ago, among other things, invented the pie chart. That's actually a relatively new invention. And this is actually a hand-drawn design that he created from data from the Industrial Revolution. So you see being compared here the wages of a mechanic to the price of wheat. To see that in these burgeoning capitalist economies, how do these things vary together? Do people get sustainable living? And along the top, we have a third data set, which shows the reigning monarch, so you know who to blame. Other classic visualizations that are really meant with this communicative purpose. This one is by the nurse Florence Nightingale, who, along with statisticians, collected deaths in the Crimean War within the English Army. And so here you see this rather exotic time series display. Here, time series are angular wedges, area and codes of value. In this case, red are deaths due to battlefield injury. Black is other, and blue is deaths due to preventable disease. So you see the major enemy of the English army was bad hygiene. And when asked why she created this weird sort of exotic visualization, for example, not using tables as her statistics colleagues suggested, she said she wanted to affect through the eyes what we failed to convey to people through their word-proof ears. So in this case, it was intentionally a form of rhetoric, perhaps making privileging the exotic over the most effective communication device in order to make a point. And of course, no visualization tour would be complete without what Tufte called perhaps the greatest statistical graphic of all time. You can be the judge of that. This is Menard's depiction of Napoleon's march on Moscow, which shows the French army advancing on Moscow and then returning decimated to sub-zero temperatures. So these are kind of classic examples of expressive visualizations originally drafted by hand that we'd like to be able to easily construct and create. We, of course, would also like a much wider gamut of visualizations from basic displays like univariate displays like bar charts and time series, but also coupled with interaction. So for example, in this case, using overview plus detail techniques to look at data at multiple scales. We'd like to explore multivariate techniques as well. So for example, here's a scatter plot matrix showing all pairwise projections of a multivariate data set. And again, we can use interaction to aid exploration. So for example, using the technique of brushing and linking, I can drag out a region in one display and then see how those data points project across all the other dimensions, thus helping engage in some form of multivariate reasoning. We can take this to other levels as well. So many of you may be familiar with the technique of parallel coordinates. In this case, visualizing a 7-dimensional data table about cars. In this case, what we've done is taken each independent variable in the data set, plotted it on its own axis, and then connected all the data points for each record or row within the table. This allows us to see correlation or anti-correlation immediately between adjacent dimensions in the display. But through interaction, we can also begin to explore other patterns as well. So for example, if I select all the heavy cars, I see that they tend to accelerate quickly, as this is acceleration measured in time it takes to get from 0 to 60. But they also tend to have horrible mileage. And I can interactively scrub and see how different subsets of the data project across all the different dimensions in the data set. Similarly, I might want to find a fuel-efficient car, so I can drag over here and then look for the things, for example, that have high acceleration as well. So in this way, I can actually navigate through multiple dimensions, in this case up to 1 or 2 dozen with this type of display interactively. These are actually all examples of tabular data, though. We can look at others. So for example, your geographic data or network data. In this case, it's both, as this is airports and the connections between them. And one thing we care about, too, is not just visual display, but interaction techniques. In this case, you'll notice that airports get selected before I even reach them, which is helpful because they're very small circles in some cases. So we actually have a hidden visualization as an acceleration structure. This is a Voronoi diagram that lets us know what the nearest point is at any given time, so we can accelerate the mouse selection that way. Here's another visualization technique. This is a network, in this case showing dependencies amongst source code files in a software project. So each node along the periphery is the name of a file containing code, and the edges show dependencies between them, and then they're grouped into a package hierarchy. And so I can mouse around and see individual dependencies, both incoming and outgoing, which allows me to assess the amount of coupling in my software design. So for example, if you're a software engineer, this might help you refactor your code to make it cleaner. Notice, though, if I drew these edges in a naive way, it's much harder to see structural patterns in the data. So what we've applied here is a nice technique called hierarchical edge bundling, where we actually use the underlying hierarchy of the software packages to help route and group the edges so that we can see bundles that lets us see how different groups actually depend upon each other while still enabling us to investigate individual files as we want to. So these are just some of the ways visualization can help us both communicate and explore data. There are many other issues as well. I apologize for this gratuitous display, but one of the things that we also care about is all the different representations we might consider for even a simple data set such as time series. And while I hardly recommend all of these representations, it is also interesting to have tools that allow us to express these various representations and the transformations between them. And then generally, like a language that doesn't let you express something silly is probably not that powerful a language in the first place. So those are all examples of visualizations. Each one of those was implemented using tools from our lab. In particular, our kind of flagship project these days is D3.js. D3 stands for Data-Driven Documents. And this is a JavaScript framework that really actually provides a domain-specific language for binding data to elements of a document. In this case, either the HTML or graphical SVG elements of a web page. So basically allows you to write rules for mapping data to visual elements and then also writing callbacks to interact with them. So this is an open source project, so if you're unfamiliar with it, you can go search for it and find it online. It's been remarkably successful, which I think is kind of something of the sign of the times in terms of both data and the ability to communicate it effectively is something of great value now. It's actually the 5th most popular project on GitHub, which is the world's largest open source software sharing site. And some of you may have used D3 without knowing it. So for example, many of the election graphics that ran on the New York Times were built with D3. In this case, showing a decision tree, showing how either Romney or Obama might win the White House, depending how different states go. And here at the bottom row, you can see in yellow the ways in which the Electoral College could have resulted in a tie. And some of you with kids or teenagers, they may have seen D3 without knowing it. This is from our friends at Stamen Design, who, among other things, create the visualizations for the MTV Music Video Awards. So this is actually D3 on the monitors here, showing real-time Twitter behavior around different musical celebrities. And so while we set out to build tools for data scientists, analysts of various stripes, we sort of inadvertently provided the infrastructure for Lady Gaga's Twitter tracker. Of course, there are many other issues in visualization. I think one really important one that's germane to this audience that unfortunately we won't talk about in depth today is scale. For example, as you end up into like billions or more of data points, many of the common interaction and visualization techniques we have no longer work. And this is not purely for computational reasons. It's also because they become perceptually ineffective due to overplotting, clutter, et cetera. So whether it's sampling or in our case, we've looked at forms of binned aggregation, they allow you to actually see densities and explore data sets that are much larger than what we can normally handle. But big challenges come up in trying to support rich interaction techniques, especially across many dimensions with those methods. And we've done some work on that as well in trying to find out ways of summarizing data so that you can maintain the same level of interactivity we see here with much larger data volumes. But now I'd like to begin to wrap up with just one last example. It's kind of moving down the chain and thinking about how visualization and statistical modeling interact. This is an incredibly rich subject, and I'll barely be able to do it justice. We already saw some really nice examples of ways they can interact, for example, in environments such as IPython, where models and visualizations can be brought together and even interacted with. I want to share one example from what we've done in text analysis. So back when I was at Stanford, we worked on a project where we were tasked with understanding how academic similarities have shifted over the years. So for example, how have certain academic practices become more or less similar over time, as reflected in the text, in this case, PhD theses that they produce. The underlying impetus was the university was spending hundreds of millions of dollars on interdisciplinary centers, and they wanted to see if this made any measurable impact in the output of the disciplines who were then kind of moving into these shared funding and shared spaces. So we actually came up with a variety of visualizations of trying to show similarities amongst, in this case, the different departments at Stanford based on textual similarity metrics. And so what you're seeing here is actually computer science in the center, and then radial distance to this outer ring is basically similarity to the other departments. These grayed out circles are those same departments at different time steps. And then those small circles in the center are actually distances to individual theses, giving you a sense of how individual dissertations might help bridge different disciplines together. And while we initially thought we'd do lots of iterations with the visualization design, turns out what instead happened is that our visualizations converged rapidly and instead revealed lots of problems with the underlying models. So we actually explored a variety of text similarity approaches. Some was just common things like cosine distance among TF-IDF word vectors. In other cases, we fit statistical topic models to basically perform a dimensionality reduction and then compare the topic vectors. So basically, get a kind of an abstracted representation and compare similarity at that level to be able to make us more robust to things like synonyms, et cetera, within the text. And this led to a variety of different models, but it wasn't really clear which one was correct. In this case, we took the similarity models and then just did a projection into 2D to try and see the structure of the overall university. And each one's plausible in its own way, but it was kind of difficult initially to be able to say which one should we prefer. And of course, the interpretation of text is somewhat subjective. So here's one example. What we came up with was clicking on a department, putting it in the center so we can see undistorted distances to all the other departments on campus. And so, for example, doing this for the English department for one of the models results in a view like this. And this was done using LDA topic vectors as for comparison, using standard techniques for optimizing the choice of the number of underlying topics. However, in this case, despite using best practices for model selection, the model is clearly inadequate as it says that all of the humanities are the same thing. With the exception of history and linguistics, apparently. I guess philosophy, too. But otherwise, all the same. So now, again, we have reason to doubt this. The visualizations brought up maybe a dubious inference that the model makes. As an assistant professor at the time, too, I was politically uncomfortable walking around showing this on campus. The humanities. So what did this lead to? So actually what happened next is we took this visualization, including particularly useful to drill down and to be able to see individual theses, and then showed this to domain experts across campus, which in this case were professors and graduate students, and actually had them annotate where they thought the model was in error. And that way we began to form some diagnostics using the visualization as a lens onto the performance of this underlying text model. And one of the really interesting things that came out of it was that it realized that regardless of different parameterizations of models, one of our fundamental assumptions was wrong. And so in this case, what we assumed was that we would have a normal distance metric, in this case, one that is symmetric, that the distance from A to B is the same as B to A.